Okay, example 3, the box. For these next 3 examples, 3, 4, and 5, we're going to kind of flip the script a little bit, and we're actually going to do the divergence theorem first, and then we're going to show that the surface integral is going to produce the same result. That way, if you're comfortable with doing the surface integral, you don't need to watch all the rest of that part. You can just skip ahead to the next one. But if you're not as comfortable with the surface integrals, I strongly suggest that you go ahead and watch how they are. And again, we're going to show that the surface integral and the divergence both work out the same. So the box, let's go ahead and do the divergence here. So the first thing we need is the divergence of f, which again, remember, is the partials dotted with f. I'm not going to write that part out again, but the partial of the first part with respect to x, of course, here is just 0. Partial of the second part with respect to y is 3y squared. And the partial of the last component with respect to z is x. So there is your divergence. So we're going to go ahead and set this up. Fortunately, the bounds are real easy. They are given to us right there. This should be really simple. So we're going to do the divergence of 3y squared plus x. The order really doesn't matter here. So we'll go dz, dy, dx. It didn't really matter. Z is going to go from 0 to 2. Y is going to go from -1 to 1. And x goes from -1 to 1. All right, so unfortunately we cannot separate these variables. So we're just going to have to go in order. So let's see here. We're going to get -1 to 1, -1 to 1. So we're going to get z times that whole thing, or we're going to get 3y squared z plus xz. And we're going to evaluate that from 0 to 2. dy dx. And let's see, plugging in a 2 for z, you're going to get 6y squared. Plugging in a 2 for the z there, you're going to get plus 2x. Plugging in 0 for z makes those go away. So this is what we're left with here. So we're still going to take an integral from -1 to 1, integral from -1 to 1, dy dx. Okay, so now we'll go ahead and do this with respect to y. So the first component is going to be y cubed. Dividing 6 by 3, we get 2. So we get 2y cubed plus 2xy. We'll evaluate that from -1 to 1. Don't forget we still have our integral of dx. Whoops. All right, so let's see. Plugging a 1 in for y, we're going to get 2 plus 2x. Plugging a -1 in for y, we're going to get -2 minus 2x. And we're going to take the integral of that from -1 to 1. dx, let's combine some like terms there. So we're going to get 2 minus -2, so that's 4. And then we're going to get 2x minus -2x, so that's plus 4x. And we're going to take the integral from -1 to 1 of that with respect to x. We could pull a 4 out, but I'm not worried about that at this point. So let's just take the antiderivative. We get 4x plus 2x squared from -1 to 1. Excuse me. Plug the 1 in. We're going to get a 4 plus 2 minus. Plug the -1 in. We get -4 also plus 2. So here we're going to get 4 plus 2 is 6. Minus, looks like -2, so we get 8. So your divergence shows us that the flux through this box is 8. All right, now we're going to go ahead and show that the surface integral is going to give us the same flux. Excuse me. And the problem with this one is that it has 6 surfaces because it's a box. We're going to show one part of it, and then we're going to start taking some massive shortcuts. Otherwise, this one could take forever. It's not hard, it just takes a long time because we have 6 different surfaces to do. All right, so let's start off with, let's just start off with the bottom of the box. Why not? It doesn't really make any difference where we start. We're going to start off with the bottom of the box. Now, I didn't sketch the box, and you can go ahead and do that, but hopefully you can see from these bounds, x goes from -1 to 1, y goes from -1 to 1, but z goes from 0 to 2. So this thing sits flat on the xy plane and then just goes up 2 units. All right, so in order to do this, we're going to need to parameterize it. So I don't see any reason why we can't just use trivial here. So x would be x, y is y, and because it's the bottom of the box, z is just 0. It's sitting flat on the xy plane. So we're going to need the cross. So we need r sub x, because remember this this part up here was the r. So r sub x is going to be 1, 0, 0. R sub y is going to be 0, 1, 0. And then we're going to do the cross product, Rx cross Ry, because we need the normal. So that's going to be eliminating the I row and column is going to give me 0. Eliminating the j row and column is also 0. And then eliminating the k row and column gives me 1. But this is the bottom of the box. Okay, this should not make any sense. This is bad. Because the z is going down, the z is going up. We want the z to go down. Well, that's an easy fix. We can just say that ry cross rx is our normal, which just changes these signs. Now, we're actually going to use this idea for the rest of these, and we're going to start taking, again, massive shortcuts once we get finished with this. Okay, we need to parameterize. We need to parameterize f. So f was y squared z for the first component. Well, that's going to be y squared times 0, so that's 0. The second component is just y cubed, so that's y cubed. And then the third component is going to be x times z, but that's also 0. Well, here's the best thing about this one right here. This right here is your n. That's your normal vector. If I dot n with f, I get 0 plus 0 plus 0. I get nothing out of that. So I'm going to get 0 for my dot product. And because I have 0 for the dot product, when I go ahead and set up my double integral of 0 dA, it's just 0. So there's the bottom. All right. Now hopefully the thing that we're going to start taking shortcuts on here is the normal vector. We know we need the normal vector to be we need it to be perpendicular, which means, and it also has to be outward facing, so it needs to be facing in the correct direction from the specific side of the box that we're on. So when we go to do the top of this, let's go ahead and write the top. I don't need to reparameterize the whole thing. The top is going to be the same thing except for z is going to equal 2. But the normal vector, this is where we're going to start to really take shortcuts, I know has to be facing straight up, which means that the z component is just 1. Okay, hopefully you're following that general idea. Again, it's the top of a box. It must be perpendicular, so the z component faces straight up. The x and y have no motion because it is a plane on the top of the box. Okay, then we're going to parameterize f. But the only thing that really matters here is what is that z component doing in f? Well, okay, I guess I did have to write the actual parameterizations here. So let's just write that x equals x, y equals y, and in this case, because it's the top of the box, z equals 2. So that actually is going to give us some kind of a value here for this. So let's see here. So if we parameterize this thing, so y squared z doesn't really matter because I'm going to dot it with 0. Y cubed doesn't really matter because I'm going to dot it with 0. The xz part actually does matter. And that here is going to be, what is that? X is x and z is 2. So we're going to get 2x. All right, so the top of this thing is going to be, let's see, the dot product is just going to be 2x. So we're going to take the double integral of 2x, and x and y are your parameters here. So we're going to have dx dy. Well, x goes from -1 to 1. Y goes from -1 to 1. So those two things can be separated. So we're going to have the integral from -1 to 1 of dy times the integral from -1 to 1 of 2x dx. The integral from -1 to 1 is just going to be the area. This piece right here is just going to be the area of the side of that plane. It's just the area of a square. In this case, it goes from -1 to 1. So that's just going to be 2. And then the second part here, we can actually go ahead and do the antiderivative, which is x squared from -1 to 1. Well, if I plug in 1 there, I get 1. If I plug in -1, I also get 1. So I get 1 minus 1, which is also 0. So the top and the bottom of this thing produce 0 flux. Okay, they counterbalance themselves on the top and the bottom. All right, let's go ahead and do one of the sides. And again, it makes no difference which one. We're going to go left and right, front and back. So again, we'll start with the left. So the left side, if you think about the left side, I guess I will go ahead and sketch this just real quick here for you. Just put this up at the top just so you have somewhat more of a visual. So here's our box. I'm not going to sketch the axes, but here's your box. It's close enough. The left side is over here. So the left side, we want this thing going in the negative y direction, because that's what the left side would be. That would be the side that you can't really see. It's hidden. This right here would be the right side. Then you've got your front, and then the back is right way in the back there. So the left side, we want to have a negative y component. So n is going to be 0, -1, 0. Okay, I will have to at least parameterize all these, it looks like. So x here is going to be x. Y is just going to be -1. And z is going to be z. That's the left side of the box. So let's go ahead and parameterize f. If I parameterize f, again, doesn't matter what I put there. Y cubed is going to be -1 cubed, so that's just -1, and it doesn't matter what I put there because when I dot these two things, I'm dotting them with 0. So here we're going to have the double integral of the dot product of n and f. That's just going to give us 1 dA. But if you remember, when you take the double integral of 1, you're just getting the area of that piece. So we're just getting the area or the surface area of the left side of this thing. The surface area of the left side of this thing is a 2 by 2 rectangle, or in this case square, because it's 2 by 2. So really that's all that this is. This is going to be the area of the domain of that thing, which is just -1 to 1 and -1 to 1. That's an area of a 2 by 2. So this is 4. Okay, you can walk through the whole process and do the double integral from -1 to 1, -1 to 1, dx and dy, or dy dx, however you want to do it. You will get 4 from that. Okay, let's go ahead and do the right side of this one. Okay, so let's do the right. So we're still going to have x equals x. In this case, y is going to be +1. And z is going to be z. Now, because it's the right side of this thing, we know that it's got to go in that direction. So it should have a +1 for the y component of its normal vector. So our normal vector is simply going to be 0, 1, 0. We don't have to go through the whole cross product in this case because we know that has to be the case. Let's parameterize it. Again, I don't care what this one is. I don't care what this one is. I do care what the middle one is. And if I parameterize it, given the fact that y is 1, it was y cubed, so that's also 1. Well, this is going to give us exactly the same thing that we just did before. We're going to get the double integral of the dot product, which is just 1 dA. Again, that's just the area of the side, so here we get 4. All right, we're getting there. Almost done with this one. So now we've done the left and right. Let's do the front. Let's try the front. And the front of this one, that means that x is 1. It's simply the plane x equals 1. Y will be y, and z will be z. Okay, again, if it's on the front now of this box, we want the normal vector to be coming off perpendicular this way, so we want the x value to simply be positive. So we know that our normal vector of this one is 1, 0, 0. We need to parameterize it. Again, I don't care what y is. I don't care what z is, because those are going to get dotted with 0. Let's go ahead and take a look at the first component, which was y squared z, which is just going to be y squared z. So we'll dot those two things, and we actually have something to work with here. We got y squared z. So we're going to take the double integral. Y goes from -1 to 1, and z went from 0 to 2. So we'll do this as dy dz. Again, we didn't have to go through the whole parameterization process because we know what the normal vector is going to be. We did have to parameterize the force, though. Okay, so let's see here. We'll take the antiderivative with respect to y. We get 1/3 y cubed z from -1 to 1. And we still have dz from 0 to 2. So let's see, that's going to give us 1/3 z minus, if we plug in -1, we get -1/3 z dz from 0 to 2. And so that's going to be 1/3 z minus -1/3 z, so that'll be 2/3 z dz from 0 to 2. So the antiderivative of that, it's going to be z squared dividing by 2 there. You're going to get 1/3 z squared from 0 to 2. So plugging in the 2, we're going to get 4/3. Plugging in 0, we get nothing. All right, so far what we have is we've got 0, 0, 4, and 4, and 4/3. We know from the divergence theorem that this thing is supposed to equal 8. Well, we've already got 8 from here and here. These two things were 0, so that should tell us that the back of this thing is going to have to negate that 4/3. It should be -4/3. Let's go ahead and just work it out just to make sure that that's actually what we get. So let's do the back part of this. So again, x in this case now is -1, y is y, z is z. Again, we know the normal vector in this case has to be pointing backwards or in the negative x direction. So therefore, it's got to be a -1, 0, 0. Again, for the force, for the y part, don't care. For the z part, don't care. The x part, I do have to parameterize in terms of this, but again, that's just going to be y squared z. That didn't change. Only thing that will change is the fact that this is now going to be -y squared z dy dz. But what I can do is I can pull that negative sign out to the front of y squared z, because negative is just a constant. And this, all of this, is what we just did for the front part, for this part right there. So the only thing that's different now is that the answer is going to be negative. So I really don't have to work the entire integral out. And hopefully you guys can see that's exactly what's going to happen. So here, this is going to give me -4/3. So when I add all of these things up, whoops, kind of forgot to put the negative in the box there. Just erased everything. There we go. So when I add them all up, I get 4/3, and negative 4/3 is 0. 0 and 0 is 0. 4 and 4 is 8. So we definitely get the same exact thing.